Right, so we've seen how we can use the heat equation together with the specific heat capacity of a substance to calculate the amount of heat that's needed to raise the temperature of a particular amount of a substance by a certain temperature change, just by substituting the values in here. Now remember, if we are going to raise the temperature of something, this would be the amount of heat that would need to be provided to the system. If this substance were losing heat or decreasing in temperature, then heat would actually be released to the environment. So we would get a negative value for the heat because our delta T would be a negative value as well. So that's something to keep in mind. And we can use that heat equation to calculate, for instance, the heat change in any of these planted regions here of our heating curve. So for example, we did an example earlier in one of the earlier videos. Somewhere along this region here, there would be a temperature change, obviously. And for liquid water, we can look up the specific heat for liquid water. We can pick any 2 points along this to see what the temperature change is, right? This would be my delta T associated with this. And then if I know how much of the liquid water I have, I can calculate what heat would be needed, what amount of heat would be needed to change the temperature by that amount. Now, we could also calculate the amount of heat needed at each of these plateau regions. Now, you will notice that in these plateau regions in pink, there is no change in temperature, right? And that happens at a phase change when we go from solid to liquid, or when we go from liquid to vapor. Any heat that goes into the system goes into changing the phase or the state. It doesn't go into changing the actual temperature. So we need to adjust, if we were to calculate the amount of heat needed for those different regions, we would need to adjust our heat equation slightly. And what we would need to invoke or to use in those at those regions would be an equation that's going to look something like this. So for instance, at the phase change boundaries, so for example, going from a solid to a liquid, which remember is melting or fusion, or going from a liquid to a gas, if that is vaporization, we know that there is no change in temperature. Okay, that's a constant temperature process. Okay. And that's referred to as isothermal. It's in temperature. Iso meaning the same, and then thermal meaning temperature-wise. So it occurs at the same temperature. So how then can we calculate the amount of heat needed for that process to happen? Well, we're going to use a slightly different equation that's going to look like this. We're going to say that heat now is equal to N, and N here would be equal to the amount of the substance. So maybe in grams, or maybe in moles, which is another unit of amount that we introduced briefly, but we didn't really talk a whole lot about. But we'll mention this a little bit later on. And then times, so the dot there means times delta H of whatever that change is. So the change here could be fusion, or it could be vaporization. And what exactly is this delta H portion of it? Well, we know what delta is. Right, delta is the change in something. And then H here is something called the enthalpy, which is nothing more than heat change at constant pressure. Okay, and when you think about it, all of the stuff that we do in the laboratory or just in general every day, that's all happening at the same pressure because it's atmospheric pressure, whatever that pressure is. So we can equate enthalpy to essentially just heat. So when we talk about the delta H and then subsequent fusion or vaporization, what that represents then is the change or the heat of fusion or the heat of vaporization. Okay, so let's try to find this out. So we can have delta H of fusion, which we abbreviate as that, and that's simply the enthalpy of fusion or the heat of fusion for that particular sample, and the FUS then means fusion. Or we can have the delta H of vaporization. That would be the enthalpy of vaporization or the heat of vaporization. Yeah, and what these values represent, these are constant values that you can look up in different tables. And what they represent is simply the amount of heat needed to melt or to vaporize a certain amount of that substance. So here we have a table of some delta H heat of fusions or heat of vaporizations for a couple of things. Let's take a look at water. I think that's the most common one that we'll come across. Okay, so here we're saying that if we're looking at water, it would take 79.9 calories of the energy to melt 1 gram of solid water or ice. It would also take 540 calories of energy, heat energy, to vaporize 1 gram of liquid water into the gas phase, right? That is what those numbers represent. The delta H is just the heat or the enthalpy of fusion or vaporization. And that is what we're going to have to use at those phase change boundaries. Actually, the heat equation gets modified a little bit. We're going to multiply that heat of fusion, heat of vaporization by the amount. And if the heat of vaporization or fusion is given in calories per gram, well, then our amount should be in grams as well. So the units can cancel out. Okay. So let's say, for example, we'll do a quick question here. So for example, let's say we had 15.0 grams of solid ice melts at its melting point. How much heat is needed to cause the melting? Okay, so the key thing here to keep in mind is we're asked for heat. Okay, so right away we're going to use one of the heat equations. And the second thing to keep in mind is that we're told that it's this thing is happening at its melting point. Actually, the melting point is where something goes from a solid into a liquid. And at that point, the temperature is constant. Okay, so at constant temperature. So that means we're not going to have a change in temperature delta T. So we're actually now going to use the modified heat equation where we have the amount N times delta H. Now, the enthalpy of the heat of melting, which is the same as fusion, right? So we're going to use the delta H fusion for liquid, for ice in this case, H2O. So we can just substitute our values. So we have our N. Our N here is 15 grams. We'll put that in. We have 15.0 grams, and then our delta H of fusion for water. We can look that up in our table. And again, you don't have to memorize these values. They'll be given to you. It's 79.9 calories per gram. That's 79.9 calories per gram. All right, so we can see how the grams are going to cancel out. I can get this calories as my unit, which is a unit of heat. So the heat there would be 15 times 79.9, and we can evaluate that. So 15.0 times 79.9 would give 1,000, 1198 1.5 calories. You have 3 sig figs here, 3 sig figs. You need to round this to 3 sig figs. Okay, so that would be 1,200, and now we're going to third sig fig calories. So the way that we would express that to the right number sig figs is we want to write in scientific notation. So 1.20 times 10 to the 3 calories. Or we could say 1.20 kilocalories. Right? We just converted to the kilo. So we could then calculate the heat needed. So remember now, this is undergoing melting. So we need to provide heat. This is an endothermic process. Heat goes into the system, so it's required for this to happen to cause the ice to melt. And we can do that calculation for any point on our heating curve, right? So for example, we would have just calculated the amount of heat in this region here to melt our ice. And once the ice is melted to the liquid, we heat it up using our regular heat equation. We can calculate the heat changes over here. Then we can calculate the heat needed to vaporize that liquid going from the liquid to the vapor by using the modified heat equation for the transition from a liquid to the vapor up there as well. Okay, so we can summarize then those delta H fusion, vaporization as follows. So the heat of fusion is the amount of heat that's needed per gram or per mole, when we encounter that, that's needed for a phase change that occurs at the melting point. Remember, fusion is the same as melting. Okay, and again, this is going to happen here at constant temperature. Okay, so the melting point has to have a constant temp. Similarly, the heat of vaporization, delta H VAP, is the amount of heat needed for a phase change that occurs at the boiling point. Again, that is at a constant temperature. There is no temperature change at a phase change boundary. And then the third one, which we didn't talk about, is well, we did talk about sublimation. We didn't talk about delta H of sublimation, but as you can imagine, there is delta H of sublimation as well. And remember, sublimation is where a substance goes directly from a solid to a gas and skips the liquid phase altogether. And each substance is going to have its own delta H of sublimation. So again, that would be delta H of sublimation would be the amount of heat needed per gram or mole of a substance required a gram of a substance for a phase change. It should be solid to gas at the sublimation temperature. Okay, so we have all those three terms that we've seen previously: melting or fusion, vaporization, sublimation. There's an energy associated with those phase transitions that we refer to as the heat of fusion, heat of vaporization, or heat of sublimation, respectively.